Okay, good morning, everyone. Where we left off last time was here. This is probably, I don't know, for me, perhaps the high point of our 4-week survey is finally when the astronomers are able to measure the parallax of a star. And that's so important because what we're really measuring is the distance to a star. Remember, from time immemorial, in studying the celestial sphere, there's no depth perception. Nobody had any depth perception from Ptolemy all the way up through Galileo, up through the astronomers of the day, like for example Bradley, the last, and Herschel. But here, with the measure of parallax, as minute as it is, we finally begin to measure distances. And this opens up a whole new realm of astronomy. So let's see how this was done. It was pursued by two great astronomers, two people, Frederick Bessel and Frederick von Struve, who really invented the field of astrometrics. Very, very detailed, precise observations. And the observations are just the raw data. You have to, what astronomers use the term, you have to reduce that data to get the actual place of the star in the sky. You have to take in consideration the refraction of light as the light goes through the atmosphere into your telescope. You have to take into consideration any proper motion that the star could be having while you're doing these observations. It's moving on its own, and you have to abstract that out. There's, of course, the great aberration of light that Bradley found, that all the stars are shifted in one direction or on the other because of the motion of the Earth. That's got to be taken out. And there are other things, the nutation of the Earth, or basically a rocking back and forth of the Earth due to the attraction of the Moon. There's all kinds of noise that has to be extracted out, and that's called the reduction of the data. And these are the two men who basically figured out how to do that. And it's their methods that essentially are still used today. Of course, it's all done with computers now, but these are the two great theoretical and observational astronomers of their generation, really of their era. Von Struve had a very traditional education, thorough, full university education in mathematics and astronomy, gifted mathematician, a gifted observer. So he was prepared for his life work. And one of the great contributions that he made in his life work was an extensive study of double stars. Remember, that was Galileo's idea: find two optical doubles, as we call them today. Two stars which look like they're close in the sky. They seem to be close in the sky, but in fact, they're very far away. One is much further than the other. So Herschel picked this up and made an extensive catalog of double stars. And he found, to everyone's surprise, that most double stars, in fact, are not optical, but are, in fact, what we call visual doubles, or binary stars, visual binary stars, where the stars are actually close together in space, and their gravity affects each other, and eventually they will revolve around each other. And from that, you can, for example, determine important characteristics of the stars, probably the most important being its mass. We'll talk a little bit about that a bit later. But what von Struve does, he took up where Herschel left off with his powerful telescopes, and he extended that catalog of double stars extensively and calculated many, many masses of the double stars, and began to get, through Struve's work, an idea of what the mass of stars were out there compared to the mass of the sun. How many stars were of greater mass and less mass? What kind of distribution of masses were you seeing? The only masses that you can calculate are from double stars. You can't do it for a single star, not at least through, because there's no motion that you can detect. It has no companion. But for the double stars, Struve created a very extensive catalog of those important stars and began to study their characteristics. Bessel, on the other hand, is a very interesting character. He is another essentially amateur for, for the incredible detailed mathematical work and observational work. He left school somewhere during high school time and began knocking around, had an interest in astronomy, found a way to start to work at a low level at an observatory. And he wrote a paper as a very young man on Halley's Comet. And that caused quite a bit of attention in the astronomical world. Who is this kid? Where does he work? Where did he go to school? Well, he didn't go anywhere to school. So he basically taught himself observational astronomy and, most importantly, mathematics. Any of you engineers out there, of course, you know of Bessel's functions. They are a very, very important set of functions in applied mathematics. Named in honor of him. He's the one who first used them in the study of the perturbation of planets, which he also did great studies of. We'll mention that a little bit later when we overall his career, at the end of his career. So these are the two men that we have. And they were looking for stars that were close, right? Because close stars would have a large parallax, would have some possibility of measuring the parallax if the stars were close. So what were they looking for? They were looking for stars which were bright. You know, bright's better than dim in terms of being close, if that's all you've got. And also they were looking for proper motion. They were looking for large proper motions. With those two things, relatively bright and relatively large proper motions compared to the rest of stars, they might be a good candidate to try to see the parallax between a January and June kind of observation as the Earth goes around the sun. Obviously, it's not just January and June. Observations are taken continuously, looking for a pattern of some kind of such a minute swing. Bessel chose 61 Cygni, the 61st star in the constellation of the Swan. It was not all that bright, but it did have a nice dim companion to it that Bessel hoped was an optical binary, as Galileo suggested that we look at. We'll see why in a minute. And it had a very nice proper motion of about 5 arc seconds every year. Remember that was found by Father Piazzi in Palermo. He was the one who measured not only the discoverer of the first asteroid, but he also studied 61 Cygni. 61 Cygni was interesting because Herschel had seen that it was in fact a nice optical double. There was a nice dim star behind it. Matter of fact, 61 Cygni was very interesting. It was a double itself. Turns out it was a true visual binary star. So there are actually 2 stars that you could see in a fine telescope compared to that back star on the back. You could get 2 measurements of the one of the doubles and the second. So 61 Cygni was a very interesting star for Bessel to pick as his study. Von Strobe was not as lucky. He went for real bright. He went for Vega. Okay, one of the very brightest stars in the sky, one of the 5 brightest stars in the sky, hoping that that was something close. Didn't have as large a proper motion as other stars, but he was hoping that the brightness would give him the closeness. And so that was a star that he chose to make his detailed study. And as the story goes, von Strobe was able to, in his preliminary studies, was able to make 17 observations of Vega. And when he reduced his data, he found that the parallax was 1/8 of an arc second, 0.125 arc seconds. Okay, remember what an arc second is. An arc second is 1/3600th of a degree. This is 1/8 of that. And he writes to Bessel. They were friends. They were friendly rivals, but there was great correspondence between them, great respect between them. And von Strobe writes to Bessel saying, you know, I've been studying Vega, and I may have something here. I only have 17 observations. Clearly, that's not enough. Clearly, I'm going to have to dedicate, you know, all of next year to get a very extensive set of observations. But preliminarily, it looks like I'm looking at about 0.125 arc seconds for the parallax of Vega. When Bessel read this from his friend, he realized, if I'm going to get back, if I'm going to get into this race to find the first parallax of a star, I better get going, because this guy is already well on his way. Ransdorf did not want to publish this anything. 17 observations was not good enough for these guys. They needed many, many more observations. There were 365 nights in a year, and 17 was clearly not enough. So he was going to wait, get more observations, and refine this number of 1/8 of an arc second. So Bessel took that as a wake-up call to really get started on his observation program on 61 Cygni 1 Cygni. And what he came up with was a parallax after a year survey of about 1/3 of an arc second. So that's a bigger angle. Okay, then that means that Cygni 1 Cygni, if these guys are right, that Cygni 1 Cygni would be closer than Vega. Vega has a smaller parallax of only 1/8 of an arc second, as opposed to 1/3. Well, what happened was that, yes, von Strobe did go on, continue with his program, took more observations, and he refined his number. He went ahead and doubled it from 1/8 of an arc second to 1/4 of an arc second. What he finally published was about 0.25 arc seconds, and that was too big. His 17 observations actually were very good. They were very accurate for a very difficult measurement. Look, he's measuring something which is less than half of what Bessel is seeing, 1/8 compared to 1/3. So he went ahead and published a number which was twice as big, and therefore much closer, and it's wrong. Vega, in fact, he was right with the 1.25. Vega is that far away. Vega is about 25 light years away. So von Strobe did not get the credit in the history of astronomy to find the first parallax of a star, because what he published was wrong. You know, as a percentage of the true value, pretty far off. Bessel, of course, was not 100%, not in 1838. You're not talking about 100% yet, but his measurement was, I believe, 90. I think the slide will show 91% accurate for that distance of about 11.4 light years is what he calculated it to be. So let's take a look. Let's take a look at what these guys did, what they were about. Here are the wonderful instruments that they used. They used the Fraunhofer reflectors. Astronomers in this day, and even to today, talk about a Fraunhofer telescope the way musicians talk about a Stradivarius. It is the gold standard. It is the most beautiful, most accurate instrument of his day. You can see this is the instrument, the 9.5 aperture lens. These are all refractors. These are not mirrors. These are all refractors to 34-foot length to this thing. This is the telescope that von Strobe used, built by Fraunhofer, the greatest, most accurate and most beautiful also telescopes of the day. We'll see more about Fraunhofer in the next presentation. And this is the instrument. Unfortunately, the original instrument that Bessel used no longer exists. So all we have are drawings of this thing. This was a different kind of an instrument. This was called a heliometer because it was first designed to measure very accurately the diameter of the sun. And so that's why it's called a heliometer. But basically, I don't want to go into the details of this thing, but it was designed to measure very, very accurately two points in space and what their angular separation was. It's exactly what Galileo said you should look for. You should look for two stars and measure how far away they are in terms of their angular measurement. Sweeping across from one star to the other, what would be the angular sweep it would take to get from one side to the other? The heliometer was designed, built by Fraunhofer to do that and only that. And this is the instrument that Bessel chose to use. Another Fraunhofer, to study 61 Cygni. You can see this tower housing that's here. Von Strohe actually helped Bessel design this thing. I say these guys were friends, and they were in a class by themselves. And this heliometer had to be mounted. You can see the couch here where you would be looking. This is way before cameras, to look and take these measurements, watching through the telescope for hours and hours. And so this tower had to be designed to be rock solid and be able to handle the mechanisms, the moving mechanisms of the telescope. And it turns out that von Strohe actually helped in the design of this structure for Bessel. I can mention here that at the end of his life, Bessel also studied the motion of the planets and other stars. And when he was visiting John Herschel, William Herschel's son, he mentioned he was studying the perturbation of Uranus. Of course, everyone was measuring Uranus at the time, still in 1842, still the great excitement of this brand new planet. And Bessel, of course, with his accuracy, saw the wobble. He saw the wobble in Uranus and left his data for people to use, like Adams and the Verrier. And he said to John Russell, "I think we've got another planet out there. The way Uranus is behaving, you guys should take a look at this. There's something out there. There's another planet out there which is causing this wobble of Uranus." So he pegged it 4 years before Uranus was discovered, which turns out to be 1846 is the year that Bessel died. So we're going to talk about arc seconds, very small amounts of arc seconds, 1/3 of an arc second, 1/4 of an arc second. I wanted to give you guys an idea of what we're talking about in terms of how far the sweep is from one side to the other. Say if you're looking through a straw and you look at one point and you sweep across with the straw to see the other point, what is the angle you had to sweep out? Imagine you're standing at the far end of a football field here by the goalpost, and you're looking downfield here to this goalpost down here, about 100 yards, 110 yards. What would be the angular separations of things that were kind of familiar to us? Well, the field itself, the width of the field, sweeping from here, from the goalpost, sweeping from here over to here, is about 30 degrees. Okay, makes sense. You can visualize that. How about the goalpost itself? Okay, from the far goalpost now, we're looking here from the far goalpost. What would be the sweep from one goalpost to the other? It's about 3.2 degrees. Okay, suppose you were standing here at the goalpost and you stretched out your arms. Okay, from fingertips to fingertips, what kind of angular separation would that be? It's about a degree, 1 degree. What is 1 arc second? Okay, you're standing here at this other end of the goalpost, and I want you to hold up a ruler. You know, with the good rulers, not just measuring an 1/8 of an inch, but measuring in 1/16 of an inch. We've all seen rulers like that. Okay, very, very nice gradations marked on the ruler of a 1/16 of an inch separation. Hold that ruler up for the person at the far end. What 1 arc second is, is 1/4 of the separation of 1/16 of an inch. Take those two very close hash marks, marking off 1/16 of an inch, and 1/4 of that is what you're measuring with your straw sweeping from one side to the other for an arc second. That's an arc second. Okay? That's not 1/3 of an arc second or an 1/8 of an arc second, which these guys are dealing with. This is 1 arc second. Okay? All right. So if I've impressed you with the accuracy that we're talking about, let's see what Galileo's idea was. His idea was find an optical double. Galileo said, find a star which is close and a star which is far. And they are aligned in the sky. They're very close in the sky. And take 2 measurements, take many measurements, but those extreme measurements of 6 months apart. Take 1 measurement here of the star. You'll see it in the sky next to the fixed star in the background at S1. Okay. you can measure that separation, the separation from your fixed star over to where you see your close star there in January, let's say. Okay. Go ahead, wait until June and take another measurement, the parallax measurement. Now the star has shifted to the other side of this very distant fixed star. That's Galileo's brilliant idea, is you'll be able to measure the shift with respect to the fixed star. Okay. Again, take a sighting from the fixed star to that second position of our close star, and that take that measurement to angle beta. Okay. What we're looking for is this angle here. We're looking for angle P. This is actually the parallax angle that astronomers use. They don't use this whole thing. They actually use 1/2. Okay, it's all the same. And the geometry is all the same. So what we're trying to measure is this angle here, P. This is the parallax angle. Okay, the angle of separation, if you were standing on the star, what would be the angular separation between the sun and the earth? If you took your straw looking at the sun, how much would you have to swing over to see the earth? That angular sweep is called the parallax angle. Again, how do you measure an angle out at a star? You don't. Okay? This angle here must have some relationships to the sides of alpha and beta, and they do. The secret is to realize that the fixed star is infinitely far away. Okay, that the light coming from the fixed star, both in January and June, is virtually parallel. These rays are coming into the Earth parallel, even though there's tremendous separation of 93 million miles on both sides. The star is so far away that these angles are virtually 90 degrees as they leave you the line of sight to look at the fixed star. With these two lines being parallel, any one of the lines of sight, I'm taking the first one, this line of sight becomes a transversal. We've seen this before with the parallax of Mars. It's the same principle. Now that we have a transversal cutting two parallel lines, we have alternate interior angles. This angle up here, crossing of the two lines of sight, imagine, there's not even a star there. That's just two lines of sight crossing in space. This is pure geometry here. Okay, there's nothing real here. But this angle here is the same as our measured angle, the separation between S1 and the fixed star. Well, how does that help us? We're trying to get P. Allow me to write one more angle. Let us put in the obtuse angle theta, okay, the angle made by S1, S, and E2. Okay, we have a triangle, alpha, theta, and beta is a triangle. Well, therefore, given the fact that we do have this transversal, that alpha plus theta is 180. 180 degrees in a triangle, right out of Euclid. Also, this is a straight line. P plus theta is a straight line, that line of sight. That's also 180 degrees. All straight lines have 180 degrees. Notice there's a theta on both sides. They cancel out. And look what P is. P is nothing more than the average of alpha and beta. Okay, that's how we measure the parallax angle. That's how it's done. Once we have P, if we can get P, if we can make these measurements accurately enough, then we can use our skinny triangle approximation. P over that funny number, 206,000 some odd, is equal to 1 over D. 1, yes, 1 AU, right? Little d is 1, and big D is the distance to the star in AUs. The units clue that we're using in distance is AU. That's why we're writing 1 for the distance from the Earth to the sun. If we solve for D, we get a very nice formula. And this is the formula that Bessel and von Strobe are going to use. If they could measure P, if they could only measure P, then they simply need to plug it in for their star and get the distance in AUs. And in the 1830s, the AU was known to be, around 86 million miles, 87 million miles, something like that. The really, really good measurement, remember, came in 1877 by the Naval Observatory of the great opposition of Mars in 1877. But in their time, the AU was known pretty well, maybe 86, 87 million miles. And you would get a distance. You might be curious to ask, what happens when P is just 1? Suppose you were standing so far away, the star was so far away that when you looked, you saw that the angular separation between the sun and the Earth was just 1 arc second. What what you get? Well, let's put one in. If you put one in, D is going to be 206,265 AU. That turns out to be 3.3¼ light years. Okay, that's the definition of 1 parsec. Okay, and we'll need the idea of parsecs in a little while. So if you're ever curious, what is a parsec? First of all, it's not a time, it's a distance. It's a distance you must stand away from our solar system so that the angular separation between the sun and the Earth is 1 arc second. Turns out to be about 3.26 light years. Astronomers find this a very natural unit to use. It's the next unit up from the AU, the parsec, which is 3.26 light years. Okay, so we go now to Bessel's measurement. Everything as it were, and Bessel takes his measurement of 61 Cygni of 0.314 arc seconds, a third of an arc second. He just simply puts P in, does his calculation, and gets 10.4 light years. 60 trillion miles. Okay. And just for fun, let's measure the proper motion of 61 Cygni. Remember, the proper motion is 5.2 arc seconds a year as it moves across our screen. Okay, it moves across us in the sky. There's no depth perception of motion still. But we do have this going laterally across us, the transverse motion. With that proper motion, another application of the skinny triangle will give us now little d, which is the traverse distance, knowing the big D. Big D being 10.4, the number that he just calculated. Little d is how much distance it'll move across our screen, across our eyes laterally in 1 year. In solving for little d, you get about 1.5 billion miles that the star is moving every year. That turns out to be a speed of about 170,000 miles per hour, which in reference, that's 3 times faster than the speed of the Earth going around the sun. So these stars are moving quickly through space. The stars are not fixed, but they're so far away that these proper motions are not detected for centuries. Okay, the way the sky looks today in 2020 is essentially the same sky that was seen by Ptolemy. It really, you'd need a telescope to know the difference. The differences are not anywhere near even 1 degree in the 2,000 years that has transpired. Okay, so that is his measurement, 10.4 light years. Turns out the modern value is 11.4 light years, 91% of the accuracy of our modern value. And through history, coming down this great rivalry between the two of them, this is the more accurate measurement than von Strobe's when he went ahead and doubled his very accurate measurement of 1.25 to 1.25, yes, to 2.25. Turns out that just a week or so later, a man by the name of Henderson, the director of the observatory down the Cape of Good Hope in Cape Town, he was studying the best candidate. He was studying Alpha Centauri, which we know is the closest star to us, about 4 light years away, even much better than Cygni Cygni of 11. And he reported a parallax of 1 arc second, 1 arc second and change. a little bit smaller than 1 arc second because it's a little bit further away than 3.26 light years, right? So if it's a little bit further away, then it's going to have a little bit smaller parallax than 1 arc second. But it's very, very close to 1 arc second. And that was a pretty good measurement. But he doesn't get the history books to say he was the first one. He was off. He missed by a few weeks of Bessel's announcement of his measurement. And so that's it. That is how it was done. And to do this, the amount of mathematics involved in terms of reducing the data, the use of the Fraunhofer telescopes, the patience, the accuracy, the precision that these instruments have to be put through in terms of their mounting and everything to take measurements that you would have confidence in this kind of difference, a third of an arc second, right? Remember what an arc second is 1/4 of the distance that you would see in the 1/8 rule, in the 1/16th ruler standing 100 yards away. Okay, so the great story of Bessel. But like I say, Bessel did much more than that with his heliometer. But before we get to that, turns out that there wasn't really many other parallaxes that were discovered for the rest of the 19th century. They're very tough. First of all, most astronomers didn't have the instruments, the great Fraunhofer machines. They also just didn't have the technique, whether the mathematical technique, the observational technique, or both. And the parallax measurements which were taken, and many were taken, of course, they were all over the lot. You took a star and you had 4 astronomers measuring the star, and you get 5 different parallax measurements. No one could agree because they're so difficult to take. And not surprising, of course, people went after the brightest stars. The brightest stars would be the easiest ones to measure if they could find a dim companion near it using these techniques. And if you look at the brightest stars in our sky, okay, this is a list of our sky in the northern hemisphere. You won't find, for example, Alpha Centauri here because you can't see Alpha Centauri in our sky. So here are the brightest stars in our sky. And if you look at the distances, there's not a lot of easy candidates here. Sirius was tried by Henderson, of all people, and he totally blew it. He got a parallax of 1/4 of an arc second with a distance of 15 light years. No, it's only 8.6 light years. Okay, the technique is very, very difficult to execute. So he just botched it and got a bad number. But as you look down, let's taking 61 Cygni as a something that was doable of about 11, 12 light years. These guys aren't helping. 37 light years. Vega, poor von Straub, picked Vega at 25 light years. A tough measurement to make. 42, 860 for the great bright star in Orion, Rigel. Okay, here's a possibility. Procyon, I think the 2nd or 3rd brightest star. I'm sorry, the 8th brightest star, one of the great bright stars of our sky, only 11 light years away. And Procyon was definitely tried. But again, there wasn't any consensus. People had measurements all over the map. And you can see maybe Altair was a possibility, but these other stars are far. They're far away. Look at Betelgeuse. Look at Deneb, right? The great star in the Swan, the brightest star in the Swan. It's a good thing people stayed away from that. 3,000 light years away. The parallax is just not measurable in their technology, and not in the technology of the turn of the century even. So this is why there was very few accurate parallaxes found really for the next 60, 70 years. These are very, very tough measurements to make. Interesting, here's the North Star. The North Star is not all that bright. I mean, it's bright enough. We can easily see it following the Big Dipper pointer stars, but it's only a 2nd magnitude star, but it's very far away. It's 430 light years away. And so it's a good thing that that wasn't tried to find the parallax of a star that far away. So it's not surprising that parallaxes were still not in very good shape by 1900. There was not a lot of consensus in people doing all the work that had to be done. The observation programs, then the reduction program to take those observations and to finally then, do the mathematics. But that all changed, of course, as telescopes became more and more powerful. We got to the 100-inch telescope in Mount Wilson, the 200-inch telescope in Mount Palomar, and of course, parallaxes began to be measured out to distances of around 100 light years and pretty accurate. But things all changed finally when you could get out from underneath, away from the atmosphere of the Earth. And that great mission first was done with the Hipparcos mission. Hipparcos named after the great Greek astronomer Hipparchus, who was the first one to use parallax in astronomy. So that first mission was named in his honor. And the idea was, as the Earth goes around the sun, to take measurements of stars and measuring that parallax angle. Here, with the great stability of the telescope in the satellite, you don't really even need a fixed star to measure against. You can actually measure these sightings directly because of this very stable platform that you're on going in orbit. And this is the orbit. Very interesting orbit for Hipparcos. Notice how eccentric it is. Okay, so not only are you going on one side of the Earth and the other, 93 million miles, but the orbit is actually quite eccentric, and it's going around the Earth every 11 hours. So every 11 hours, you're way out here. Okay, at its perigee, at its closest point, it's only 310 miles above the surface of the Earth, but way out here, it's 22,000 miles away from the Earth, and that every little mile helps. So not only are you 93 million miles away, but you also can tack on another 22,000 miles. And given the accuracy of these telescopes, that actually helps a little bit. So it wasn't bad to have this very eccentric orbit. What I recently found out when I was reviewing the Hipparcos Mission, I was surprised to read that this orbit actually was a mistake. Turns out that they wanted quite a circular orbit, but there was a defect either in the calculation of the burn or in the burn itself, in the mechanics of the burn itself, and it threw it into this highly elliptical orbit. At first, the people at the European agency, the European Space Agency, who put up Hipparcos, this is not a NASA mission, but a European Space Agency mission, they were like frozen in panic that the thing had gone wrong, and God knows what orbit this would be, even would have gone out of orbit and drifted off into space. When everything settled down, they realized that they had this highly elliptical orbit. They said, well, okay, we can deal with that. That's fine. But it actually was a mistake to have this orbit. And I was asked in our class when I first talked about Hipparcos and mentioned this mission as the first user of parallax, how do you get such an eccentric orbit? And at the time, the answer I gave the class back in the fall was, well, you're just going to have to wait until we get to Newton, because Newton is the one who's going to explain how we get these elliptical orbits. So now I think I can make good on that promise of explaining how do you get an elliptical orbit or any orbit. What determines the eccentricity of an orbit of an orbit of a satellite? Turns out it's a balance between the distance that you are, the average distance that you are away from the central body, and the speed that it's going at. The balance between those two things will determine the eccentricity. The distance is determined by the potential energy of the satellite. The speed of the satellite is determined by its kinetic energy, and by balancing the kinetic energy and the potential energy of the satellite, the mathematics you can then calculate what falls out of that balance is the eccentricity of your orbit. And so, if you want to have a highly eccentric orbit, you just adjust that balance of potential and kinetic to get the value of eccentricity that you want in this exercise in celestial mechanics, all following Newton's laws. Okay. The mission ran for 4 years, from 89 to 93, and by the time the reduction of the data was done, yes, the reduction data, even out there has to be the reduction of the data. The raw data is worthless. It needs to be reduced to comparing apples to apples, and a catalog of 118,000 stars, from 100 stars in 1900 to 1995, when this catalog was published, to 118,000 stars, done to a precision of 1,000th of an arc second. Think of it. This is the kind of precision that was done when you're way up high in space without any interference from the Earth's atmosphere. And the calculations were good out to 300 light years. Yes, only 300 light years. You can't go infinitely far away. You have a baseline. You have a baseline of 93 million miles. The geometry is only going to give you, with an accuracy of 1,000th of an arc second. It all sounds very good, but the geometry breaks down at some point. You don't have the accuracy. You lose all the decimal points when you do the math. And the furthest out you're going to get with 1,000th of an arc second of accuracy and 93 million miles on one side of your baseline, the best you're going to do is about, with that accuracy, of 300 light years. There are many, many objects in the sky that we know are much further away than 300 light years, right? 300 light years hardly gets us out of our neighborhood. 300 light years is not anywhere. It is just a local neighborhood of the Milky Way, right? The Milky Way is thought to be 100,000 light years across, 100,000. So what the Hipparcos mission was able to do, and there have been subsequent missions after that, which has extended the 300 light years to 3,000 light years, I think is the maximum that we have today using straight parallax. But there is a limit to what parallax can do. There's a limit to what the geometry can deliver. But this was the first great mission to use parallax putting the camera out in orbit. Okay, wanted to mention one more thing about Bessel's career. Well, two things actually. One is I already mentioned the fact that he was looking at Uranus and saw that there was a perturbation caused by something else. Another thing was he made very accurate measurements for the moons of Jupiter and Saturn. And if you go back and take a look at our first presentation, that's how you find the mass of a central body. So we have Bessel to thank for the modern accurate measurements of the mass of Jupiter and Saturn by studying very detailed the orbit, the period, and the average distance, the A value, the major axis value of some of the great moons of Jupiter, and able to make those calculations for the mass of Jupiter and Saturn. But also what he's very famous for, his other great discovery, was in studying two very bright stars, the brightest of all, Sirius and Procyon. He noticed that they were wobbling. As he watched them year after year, he noticed, for example, with Sirius, that Sirius, you can see Sirius A, as it's called, the very bright star in the sky, our brightest star. The yellow trajectory had a wobble to it. What would cause that? And of course, Bessel realized that what was going on was there was a companion star, what he called the dark star, because he couldn't see it. All he could see was the wobble of Sirius. And he was able to make some calculations and make some estimates of just what kind of mass and what kind of distance would that dark star be to create that wobble of Sirius. Of course, you're quite free to choose what parameters you like. If you choose a certain different mass, well then you'll need to have it at a certain average distance to get the observed wobble. If you pick a different mass, then you'll need a different. So he was able to make calculations of what possible candidates they could be. He had no way to determine. All he could see was simply the wobble. This is something that he left for posterity, that there was definitely this was a double star. This was a binary star, and it's a new category. It's called an astrometric star because we know that there's the double by the motion of the visible star. We only see one star as opposed to an optical or a visual double. This is an astrometric binary in which we only see one star, but its behavior, its motion tells us that there is in fact a second star. And so we have our third category of double stars: optical, visual, and now astrometric. Turns out that was found, that dark companion was found in 1862 by Alvin Clark. I want to make a mention here that we're beginning to mention Americans here and there, right? The first mention was with the great meteor shower, the Leonese shower. I'm sorry, now I forget his name, of 1833. He was an American teaching at Yale, was the one who figured out that what was going on was the Earth was moving through some kind of a cloud debris system, and that's what the meteor shower was. And then, of course, we have the observatory, the Naval Observatory of 1877, where that observatory, that man discovered the 2 moons of Mars. And also participated in the parallax of Mars, another American. And here's a very important American for us here. This is Alvin Clark and his sons. They took up where Fraunhofer left off. They began building the biggest, most accurate refractor telescopes, beautiful lenses, beautiful pieces of glass, bigger than even what Fraunhofer could achieve in his technology. These are the guys who pushed the technology further of creating these perfect lenses that had minimal chromatic refraction. They're breaking up light into colors, keeping everything focused in one point. And he built the great 18.5-inch refractor, the biggest refractor in the world. And these people stayed as leaders of building refractors really until the refractor age ended around the 1880s and 1890s, when the technology got to the point where you just couldn't build glass any bigger and still would be practical. The glass was so heavy and the focal length was so long that the tube had to be so long with this incredibly heavy piece of glass out in its end, it was no longer stable. The building of refractors really came to an end. Bigger and bigger refractors came to an end, and it was when the reflectors then took over for professional astronomy. But the Clarks, his son, took over the business from him, and they continued to build. And the world came to them the way they came to Fraunhofer 30 years before, if you wanted the biggest, most perfect refracting telescope in the world. Anyway, the story goes he was testing his new 18.5-inch refractor, and he saw this little dot. Here's, of course, a Hubble picture, but there it is. There's Sirius B. There's Bessel's dark companion, dark star. And he, he's a telescope maker. He's not a professional astronomer, but he saw this thing. I don't think as clearly as this Hubble picture, but he saw this thing in his refractor and didn't know really what to make of it. So he called up George Bond, the director of the Harvard Observatory. They were in Boston. They were in Cambridge, is where their shop was. And he mentioned that I saw this thing. Is this like important? And Bond was bowled over. Yes, you just found Bessel's a dark star. You found the binary of the brightest star in the sky. And so the Sirius went from just an astrometric binary to also a true visual binary star, when the telescopes got powerful enough to see it. Very interesting star, this Sirius B star, very, very dim. Sirius is about twice as bright as the sun, whereas Sirius B is just 1/20th the brightness of the sun. But what's interesting is Sirius is about twice the mass of the sun. Sirius B is the same mass as the sun, but it's so dim. It's because it's only the size of the Earth. Here we have a star which is very, very dim, has the mass of the sun, but only the size of the Earth. We call these now white dwarfs. And Alvin Clark is the first one to discover a white dwarf. He, of course, didn't know it was a white dwarf. It was just a dark companion. By the way, when Bessel talked about this at first, back in the 1840s, that there was this dark companion, this dark star, some people were very skeptical. What do you mean a dark? There's no such thing as a dark star. Isn't that like a contradiction in terms? And Bessel said, no, there's no reason why everything in the universe has to shine like that. That every object that we see has to shine. That has to have its own. Some things can just be not illuminated at all. That's possible. So he had the imagination to see that, and the white dwarfs are certainly the most important example of that. So what does distance give us? Distance gives us the ability to finally compare the brightness of stars. because we know how brightness in our eye falls off by distance. As something gets further and further away, it gets dimmer and dimmer. It falls off by 1 over the distance squared. Yeah, isn't that amazing? Just the way gravity falls off, just the way the the electrostatic force of two charged spheres fall off. If you double the distance, the force drops by a fourth. If it's a light source, the brightness of the light will drop by a fourth. If you move something 10 times further away, the brightness will drop off to 1/100th of that original brightness. Since we know how the brightness works with distance, when we look at all the different brightnesses in the sky, we can then set up a system that we can imagine they were all put at the same distance. Imagine putting all the stars at the same distance. Then what would their brightness be? You can calculate that because you know what if you know what their visual brightness is, how bright they look to us, and how far away they are. You have to know how far away they are so you know how much you're moving them by so they all get to that same common distance. So you can measure apples to apples. And the man who did that system of actually being able to measure pretty well, this is before photometers that we have now in cameras, but here in 1856, a man by the name of Norman Pogueson figured out how to do this very nicely, how to take two light sources and say, which one is brighter than, is it twice as bright? Is it 3 times as bright? Is it 3.27 times as bright? How do you do that? He was able to devise the first mechanism to make that happen. And basically you take standard sources of light. You take a standard bulb, okay, taken very, very simply, and you put it on a screen. And at the distance 1, you know, that's certain brightness. Well, then go ahead and move it twice as far away. Well, now take that brightness, compare it to the first brightness, that's 1/4 the brightness and 1/9 the brightness, you know, and you can get a whole, of course, a whole spectrum of this. And this is what Pogueson, he created a system that we all could talk apples to apples in terms of brightness. And then how do you measure the brightness of a star? Well, you take that series of lights, okay, that he has now calibrated, and you put that light in your telescope eye, and you put your star in your eye, and you look at the artificial light coming from that standard distance of that standard bulb that you know was called a brightness of whatever X, and you look at the star, and you change your standard brightnesses. You change from one little you know, round circle to another until you finally find a light which is to your eye the same brightness as your star. That's the brightness of the star. That's the apparent brightness of the star. Okay. It's not perfect. Of course, it's not a photometer where you're measuring photons, but for 1856, it was pretty good. It was a good start. And that was just the first mechanism. There's a number of mechanisms that were developed. One was how much a shadow could be cast by a light. Very clever way of doing it. And the depth of the shadow, the darkness of the shadow was calibrated to the brightness of the light. There was a number of different ways of doing this. Very interesting science to all this. But after all is said and done, what we have is a apples to apples comparison of the visual brightness of stars. And this is the scale down below that you can see. The brightness of we can see goes from well, Hipparcos started with a magnitude 1 star down to a magnitude 6 star. I know the numbers go backwards. The brightest stars are the first magnitude, and the dimmest stars are the 6th magnitudes. Everything's going to be backwards in terms of the size of the numbers. Well, Pogueson then just went ahead and spread this thing out by measuring how much brighter things are. And for example, the sun turns out to be a brightness of a -27, way beyond a brightness of 1. Vega is taken as a standard generally. Vega is taken as a magnitude of 0. And so the system that Pogueson worked out mathematically was, the law is, if something is 5 magnitudes different, then it's 100 times difference. So the difference between a 1 magnitude star and a 6 magnitude star, a 1 magnitude star is 100 times brighter. With that mathematical definition, you can lay out a scale. The details are nerdy, it's unimportant for us. But that fundamental rule gives mathematicians the ability to lay out a scale like this. So our eye limit goes to about 6 magnitude stars. And you can see various stars, of course, that we can see. The Hubble telescope can see down to around 30, magnitude of 30. Quite incredible. And here are the apparent magnitudes of some of the great bodies in the sky. Notice that even the Andromeda Galaxy has an apparent magnitude. Yes, it is in the visual range. If you know where to look, binoculars are better, but if you know where to look, you can see the Andromeda Galaxy with the naked eye. And what's really cool is you can see it with binoculars quite nicely. If you can see it, you want to look that up in Google, how to find the Andromeda Galaxy. It is pretty cool. You're looking at the furthest thing away that you can see with the naked eye. 2.5 million light years away. Okay. Notice that Uranus on a good night, if you've got young eyes, you can see Uranus at its maximum. Okay, maybe. But Neptune is below our visible range and Pluto is below our visible range. So that's just the distance drop off. With this scale, knowing how the brightness drops off with distance squared, when you know the distance and you know the apparent brightness, Pogeson could make this scale. And so here's a very interesting picture. Here we have Sirius in the Dog star, the Dog constellation, Canis Major. And this is the brightest star in the sky. And these are the apparent magnitudes of the great stars in the Dog star, where Sirius, the bigger the circle, the brighter the star. Take a look if you all move them out to the same distance away, and you measure what we call their absolute magnitude. Push them all out to exactly the same distance, and then ask, then how bright would they look? And you can calculate that if you know the distance of these stars. If you know their apparent brightness and their distance, you can push it out or in, if you like, to some standard distance, put everybody on the same rim of the same circle, and then ask, how bright would they look? And look what happens to Sirius. Sirius is, even in the Dog star, is not the brightest star in that constellation. It's these stars down here are actually brighter, okay, inherently brighter if they were all at the same distance away. And this brightness, the brightness that we measure when they're all the same distance away, pick a distance that we're all happy with, that we all can live with, and find out what their apparent brightness would be at that distance. That's called the absolute magnitude of the star. Okay? And very interesting picture of if we took all these different stars, of how we see them with our eye, and put them all on the rim of the same circle, this is the brightnesses that we would see. Okay? And what is that standard distance that all astronomers want to use? 10 parsecs. I don't know what the parsec thing, but they love parsecs. So you push everybody out 32.6 light years away, and then see how bright they would be. And that is what you call the absolute magnitude of a star. So if a star was further away than 10 parsecs, and it had a certain magnitude, say it had a magnitude of 5, well, then when you brought it closer, right, it would get brighter. And so its absolute magnitude would be brighter, but that's a small number. We go from magnitude 5 down to a magnitude 3. Yeah, the whole thing is backwards because of Hipparcos with his first magnitude stuff, but astronomers love their history. They didn't want to change what Hipparcos did fundamentally. So we have this magnitude system where very small numbers are bright and very big numbers are dim. And the same thing if a star was very close and you push it out to 32.6 light years, it would get dimmer. And so its apparent magnitude would be, its magnitude would be less, its brightness would be less, and so its absolute magnitude would be smaller than what we see by our eye. And for you math types, here is the formula that if you know the apparent magnitude and the distance, you can in fact calculate mathematically what that absolute magnitude would be. It's a formula which uses the log function, but you simply put in the distance and the apparent magnitude, and you'll get the absolute magnitude. Notice the simplest of all, if D was 32.6 light years, if your star was at that place, right, then your absolute magnitude would be your apparent magnitude, because you are at the place that they want everybody to move to. And look what look what you would get if d was 32.6. This would be 1. The log of 1 is 0. 5 times 0 is 0, and sin capital M would equal little m. So the formula works for the simplest case, and you will trust the astronomers and mathematicians that it works for all the cases. And so here are the absolute magnitudes of some stars. Notice the sun does not do very well. If the sun was put at 10 parsecs away, it would barely be a 5 magnitude star. Sirius is a bright star, still continues to be bright, but not like the minus 1.4. It falls down to 1.5. Here's a bright star. Vega is a bright star. Okay, even moving Vega at 10 parsecs, it is still just a half 0.5 magnitude. And look at Polaris. Look how bright Polaris is. It is a minus 3.62 star. It is brighter than what Sirius looks like to us. Much brighter, 50 times brighter, and 2,000 times brighter than the sun. And finally, look at the Andromeda Galaxy. It has an apparent magnitude of 3.5, quite within the visual range, but it is so far away, 2.2 million light years away, that look at its absolute magnitude. Its absolute magnitude is a minus 20, okay? And interestingly, then relative to the sun, what is that? It's about 15.5 billion times the light of the sun. And that's not a bad number as an average of how many stars there are in the Andromeda Galaxy. There are in fact more, but most stars are not as bright as the sun. There's a lot of stars brighter than the sun. There's a lot of stars dimmer than the sun. So on average, if all the stars were averaging the luminosity of the sun, you'd get 15.5 billion of those suns that make up the Andromeda Galaxy. The Andromeda Galaxy is more like 100 billion stars, because many of them are not as bright as the sun. Okay, so are there any questions? I'm looking at the chat. If you have a question, if you want to type something in while I fumble around closing this and opening up our last presentation. Where am I here? Okay, I think this is us. I see nothing on the chat. Okay, very good. So not, not that it's very good. I didn't mean that. That came out wrong, guys. I'm sorry. All right. So our last presentation, let's just get started with this. There was kind of a method to my madness here in our 4-week survey. I really took 3 themes to survey the history of astronomy from 3 points of view. Our first presentation was on the solar system. We looked at the planets and the comets and the asteroids and the shooting stars and all the things which happen within our solar system. We just finished our second presentation was what the developments were about the stars. And we went a little bit further. We went into the 1860s, but that's okay. We wanted to kind of come to a natural starting point, ending point. Here I'm going to do the same thing. We're going to go back again. Just as in the second presentation, we went back. Actually, went back to to Hadley, to Halley, with his proper motion. We're going to go back again now for this last presentation, this last focus, which is on light itself and the analysis of light itself. And this will open up. This will just open up a whole new dimension. This will bring us to modern astronomy. At the end of our presentation here next week, we will be at the doorstep of modern astronomy, or what was called at the time, at the turn of the century, the new astronomy, as was called, very reminiscent of the great work of Kepler, of Astronomy Nova, his new astronomy. This is just as new, just as groundbreaking as what Kepler did with his Kepler's 3 laws. And it's all about the analysis of light. It's all about taking light and breaking it up into its colors and seeing what we can learn from the source of that light by the colors that it gives out at its different brightnesses, because not all the brightnesses will be the same. Not all colors will shine at the same brightness. If we can see what colors are shining and what their relative brightnesses are, can this tell us something about the thing that is shining, that is glowing with this light? And the answer very much is yes. There's a tremendous amount that can be learned from the analysis of the light of a glowing source. Okay, so we'll go back to the beginning. Again, we'll go back here to Newton. The three great properties of light that we want to remind ourselves of is the property of reflection of light, which of course gives us our great reflective mirrors, telescopes. There's the refraction of light, going from one medium to the other, whether it's glass or air or water. This allows us to build our great refractors, our lens telescopes. And then there's the dispersion of light. This is what we're going to focus on now. And that when light goes through, that the different constituents of light, which turn out to be the colors of light, refract at slightly different angles. They bend at slightly different angles depending upon their color. And so they will spread out as they move in space from that initial refractive point. And that's what we're going to focus on. This phenomenon, that the colors will spread out so that we can see them, because they're being refracted at different angles. For some reason, the colors are refracted at different angles. We get this effect. And we can use this effect to study what was called the spectrum, a word coined by Newton himself, the spectrum of the light. And here is Newton, the famous experiment in which he first did this. Of course, this was not unknown in Newton's time. Everyone was refracting light and beautiful crystals going back to the Egyptians. We have beautiful crystals, refraction glass ornaments back in ancient Egypt. But what Newton did was, in the refraction, he showed two things. He showed if you take one color and you try to spread it out, you can't. That if you isolate a color like red and you try to put it through another prism, it won't spread. The red is the red. Okay, there are these different kind of almost individual constituents of color to the sunlight, to the white light. And the other thing, the most remarkable thing that he showed, was after he was able to disperse the light, have the dispersion, he was able to bring them back together, back to the original white light. And this picture here is the proof that the colors are not some kind of, I don't know, effect that the light is being, doing something weird. No, the colors are the light, are the white light. All these colors together, our brains, when these all colors come to our eye at the same time, we see what we call white light. And the camera and the screen and everything else sees what we call white light, because you can break it up and you can put it back together again. If you put those colors back together again, you get white light. There were two theories of light in Newton's time. Newton had the particle theory of light. He was a particle man. And the particles bouncing off of a surface certainly explained the law of reflection. And even he had a very nice theory of why particles would change their direction going through a different medium. They would change their speeds in certain ways. And so his particle theory could explain the refraction of light. Huygens had the alternate theory of waves, and the wave theory could also explain reflection, and the wave theory could also explain refraction. One interesting question: what was color? What was, how do you explain color? Well, Newton said that since light was made of particles, that color was different masses. Different mass light particles had the different colors. And so when they entered your eye, the colors of different mass would strike us in our brain as different colors. Huygens said no, in the wave theory of light, it would be the frequency or the wavelength. They are related to each other for light that moves at the same speed. And there's a simple relationship between frequency and wavelength. It is the frequency or the wavelength of light that's creating the colors that we see, that composition of light in a dispersion. Well, these two theories moved on simultaneously. The authority of the two greatest scientists of their age. And it wasn't until 1801 that this was finally decided, at least for a while, until the quantum effects kick in the beginning of the 20th century. But what Thomas Young was able to show in 1801 was that waves do this, that particles don't do. Two waves at the same place at the same time can what we call interfere with each other. That is, if two crests come to the same place at the same time, you'll get a double crest. So if it's a water wave, you'll get a wave which is twice as high or twice as low in the trough. And if the crest meets the trough of two equal waves, you'll get no wave at all. You'll get calm water at that place. And if the crests and troughs continue to come into each other simultaneously in phase, as it's called, that water will remain calm even through this whole ripple. Everything is rippling all around it, but there will be lines of calm water. Thomas Young was able to show that was so for light. And I really encourage you to take a look at that, the video that I suggested, that 8-minute video about the reproducing Young's original experiments. Very nice explanation of interference. Very, very nicely done video. I highly recommend that if you haven't seen it before. If you've taken it in my other classes, you will have seen it because it's one of my favorite demonstrations of this interference effect. So I mentioned frequency and wavelength. Let's just take a look at those again. First of all, we have the crest of waves and the troughs of waves. We have the wavelength from crest to crest or trough to trough, the wavelength of a wave, and finally we have the amplitude of a wave from the equilibrium point up to its highest disturbance. These are the pieces of a wave, the anatomy of a wave. The amplitude we won't be talking about too much, but the amplitude is, of course, the brightness of the light. It's the power of the water wave, the height of the wave. So this is what measures the brightness. And we'll see that different colors have different brightnesses depending upon who's making the light. But what's most important for us is the frequency or the wavelength. And notice there's clearly a relationship. For a low frequency, what do I mean by a low frequency? I mean, imagine all these waves are moving in this direction. Okay, they're moving from left to right, and you're standing in one spot. If these waves are moving across, if you count how many crests pass you by, if it's a low count, that will be a low frequency. That the frequency of how often you see a crest as the wave passes you by is small, relatively small. That's a low frequency. Here would be a medium frequency, and here would be a high frequency. All these waves, we're thinking of them now as moving at the same speed. And so as they pass you by, clearly many more crests will pass us by in the same time for this wave than for the top wave. This has a high frequency, okay? And clearly it has a small wavelength. We use the word short and long. These are all come out of basically acoustical terms, why we use these words. We don't talk about small wavelengths. We talk about short wavelengths, okay, or long wavelengths. We don't talk about long or big frequencies or small frequencies. We talk about high frequencies for large frequencies and low frequencies. These all come out of the equivalent of sound waves. Okay, so there is a beautiful relationship between frequency and wavelength, as you can see. A low frequency has a long wavelength, okay, and a high frequency has a very short wavelength. Okay, this is for waves moving at the same speed, which would be true for us, okay, because all of our waves will be moving basically through space, coming into just a simple air to be analyzed. Okay, so that we can come to a natural stopping point here. We'll go back to Herschel and his discovery of infrared light. So we will stop there. Okay, guys, I will get us out of share mode, and here we all are. I will unmute everybody. Let me do that. Okay, you are all unmuted. And as you leave, are there any questions that I can answer before you guys take off for the day? Questions?
No, not here.
Okay.
Thank you very much.
All right, guys,
Thank
have a
you.
good day. Our last class is next Friday, and our last seminar is this Monday. So if you haven't been to a seminar and you're curious, come on in this Monday. It's your last chance. All right, guys, have a good day.